Okay, again, this first part is going to be a torque times time is moment of inertia times change in angular velocity. And again, we have some of the pieces here. We've got the torque, right? So 31 meter newtons is our torque. The time is what we're trying to solve for. And then it seems like we can figure out the moment of inertia from all that stuff, right? And then this is our change in angular velocity, right? 5.2 radians per second. And this has to be radians per second. That has to be meter newtons. That has to be seconds. This has to be kilogram meters squared. Don't try to do it any other way. All right, so now let's figure out the initial angular inertia, right? The moment of inertia. So initial is, we're going to use 1/2 mr squared for the merry-go-round. So 1/2, what's our merry-go-round? 140, right? It's a cylinder, and then it's 3.3 meters, right? And then the child, we're going to say that the child, all of the child is at 2.7 meters, right? We don't spread the child out into a cylinder. That's cruel. All right, so 68 times 2.7 squared, right? So if they say there's some object at a particular distance, use the mr squared formula. If they say it's a cylinder, well, I use the cylinder. In reality, the child would, anyway, it'd be a little bit more complicated, right? But to the extent that the child is small compared to the merry-go-round, it's not a big difference. Okay, so 0.5 times 140 times 3.3 squared plus 68 times 2.7 squared is 1258.02 kilogram meters squared. That's our initial moment of inertia. So 1258.02. And now we're ready. We can solve this. Go this times this. So times 5.2 divided by 31. And I guess we're solving for time. So time is 211 seconds. It's a long time. It's like, how many minutes? It's almost 4 minutes. All right. Just pushing it away. All right. Okay. And then now down here, we want to use I1 omega 1 equals I2 omega 2. Okay, so to do that, we've got to find the final, and that's going to be this, the merry-go-round doesn't change. So 1/2, 140, it's a cylinder, right? 3.3 squared, right? And then the child moves in. They were at 2.7 meters, right? And now they're going to be at 1.9. It's exciting. It's an exciting development. So 68 times 1.9 squared. So again, if they say an object of a certain mass is at a particular position, use the mr squared one. If they say it's a cylinder, if it's a sphere or whatever, use the appropriate formula for that. Okay, so let's do this. I'm going to go up there to that thing. I'm going to change my 2.7. So I went up arrow to that expression. All I have to do now is change the 2.7 to 1.9. And I get 1,007.78 kilogram meters squared. Okay, now I can do I1 omega 1 is equal to I2 omega 2. This is conservation of angular momentum, right? Okay, that we decrease our moment of inertia, therefore we will have increased our angular velocity. So let's see. Okay, so when it's spinning, so this is our initial angular velocity, I think, right? It's already going that speed. So I'm going to go 1258.02 times 21 RPM. I'm just putting RPM in there. Watch. Okay, equals, you can do this, right? 1,007.78 times what is the final angular velocity, right? All right, so this times this. I'm going to find the 1258, enter, times 21 divided by the number I just got. Boom. And I get 26.2. And that's RPM, right? Notice that these are both kilogram meters squared. Those units cancel out, and I end up with omega is 21 RPM times a pure ratio, right? So the answer is going to have the units of RPM. You can, if you put in RPM into this thing, you'll get RPM out. If you put rotations per second, you'll get rotations per second out. If you do degrees per year here, you'll get degrees per year out. Okay, so that's kind of a cool thing about this. Yeah,